Today I'm going to present to you our paper, Sparsity in Covering Solution, authored by Dr. Pallavi Jain and me, Manveer Singh Rathore. Two of the well-studied covering problems are vertex cover and feedback vertex set, and these are the problem focused on in this paper. So let us first look at what vertex cover is. In simple words, delete vertices such that no edge remains in the resulting graph. In other words, pick a set of vertices such that no two unpicked vertices have an edge. For example, in this graph, if we pick 4 and 5, then as we can see, none of the unpicked vertices have an edge between them. Now let's come to sparse vertex cover. In sparse vertex cover, we pick a set of vertices of size less than or equal to k such that no two unpicked vertices have an edge and edge between picked vertices are less than or equal to t. For example, in this graph, if I pick 4 and 5, then edge between 4 and 5 is 1. So if t is greater than or equal to 1, then we are fine from the edge side. And if k is greater than or equal to 2, then we are fine from the vertex number of vertex size side. And now if we pick 4 and 6, then the edge between them is 0 and the size of vertex cover is 2. So if k is greater than or equal to 2, then 4, 6 is fine because for any t, it will only have 0 edges. Now let's come to feedback vertex set. In simple words, delete vertices such that no cycle remains. Or in other words, pick a set of vertices such that every cycle passes through at least one of those vertices. For example, in this graph, if we pick 5, then as we can see, all the cycle passes through the picked vertices, or if we delete 5, then there are no cycle in the remaining graph. Now let's come to sparse feedback vertex set. In this, we pick a set of vertices of size less than or equal to k, such that every cycle passes through at least one of those vertices, and edges between picked vertices are less than or equal to t. For example, in this graph, if you pick 5, then there are 0 edges within the picked solution, and it is FVS. So this is the best feasible solution for any sparse feedback vertex set constraint. Now let's come to classical complexity of our problem. So vertex cover and feedback vertex set both are NP hard problems, but there are two more problems: independent feedback vertex set and independent vertex cover. So basically, our problems are the generalized version of independent problems. And if we put t equal to 0 in our constraint, then our problems become the independent version. So for independent vertex cover, we know there's a polynomial time, it can be solved in polynomial time, and there's a polynomial time algorithm. But independent feedback vertex set is an NP hard problem. So now let's understand what parameterized complexity is. So in parameterized complexity, we have a problem, and each instance of that problem is associated with an integer k, which is known as parameter. Our goal is to design an algorithm with running time in function of k into a function polynomial in n. And before going into the algorithm, we pre-process the data efficiently, and that is called kernelization. So what kernelization is? We reduce one instance of that problem to another instance of the same problem where this I dash plus k less than or equal to function of k, and that reduction is done in polynomial time. So the existing results for vertex cover is a linear kernel and 1.25284 to the power k time algorithm, and our result for sparse vertex cover are a quadratic kernel and a FPT algorithm for SVC in 1.3953 to the power k. And for FVS, as the existing algorithm is 2k quadratic kernel, and FPT algorithm for 3.46 power k. And for our SFVS, we have k to the power 4 kernel and 5 to the power k algorithm. So let's start with sparse vertex cover kernel. So for example, we'll take this graph and k is equal to 4. So first of all, we will delete all the independent vertex in the graph since they won't be contributing in any minimal vertex cover. So we will delete those independent vertices from the graph. After that, our graph looks something like this. Now we will mark all the vertices that either have a self loop or have k degree more than k plus 1, or we have, in other words, have more than k plus 1 neighbors. So we'll mark those vertices as m. Now we'll add a k plus 1 size set of vertices named SV. So now our graph G looks something like this. And after that, we will add an edge between each vertex of M and each vertex of SV. So after adding the edges, our graph looks something like this. And now we'll mark SV also as M. After that, all the vertices that have only have neighbors in M, all the vertices in G minus M that have only neighbors in M, like these two vertices, we'll delete those two, and our graph will look something like this. After that, we will delete all the self loops that we have in our graph. So as you can see, we picked this vertex in M that had a self loop. We'll delete that self loop and not other edges, only that self loop. Now our graph will look something like this. So this M, we know it is of size at max. SV was of size k plus 1 and M was also of size at most k, because since each vertex of the original M have to be in the solution since they had k plus 1 neighbors, or else their neighbors would be in solution, and we know that that is not possible since they have k plus 1 neighbors. So M is of maximum 2k plus 1 size, and now we have to find the size of G minus M. But since we have a degree constraint on G minus M, that highest degree in the graph cannot be greater than k, since all the vertex having degree k plus 1 we have already picked in M. So we have a kernel on our graph, which is number of vertices in G is equal to number of vertices in G minus M plus M, and number of vertices in G minus M is k square plus k, and in M it is 2k plus 1. So overall we get a kernel of k square plus 3k plus 1. Now let's come to sparse vertex cover. First, we define a new problem, constraint sparse vertex cover, and we'll prove that they both are just equivalent. So in constraint sparse vertex cover, there's the input, a graph G, a set X subset of vertices of G, and a non-negative integer k. The question is, find a set S from S0 to Sk such that for each I belongs to 0 to k, if G minus X does not have a vertex of size exactly I, then Si is equal to Z. Otherwise, Si is a vertex cover of G minus X of size I that maximizes sparsity. So this might look a little difficult definition. If you go through it again and while pausing the video, you might be able to understand it. So now we'll solve this by dividing the problem in different instances. So first of all, there are polynomial time solvable cases. So if a graph has a path, then that path is a polynomial time solvable. And if that is of limited size, then also it is polynomial time solvable. And if it has only one vertex with degree more than 2, then also it is polynomial time solvable. So now we'll go with divide all the components in the graph in different categories, and for each category we'll have a different time complexity, and the worst from all of them will be complexity of our problem. So as we said, this is polynomial time solvable, and it's because we have a dynamic programming approach for this one. And these two cases, we can just simply branch on the high degree vertices, and the remaining graph will become paths. So we have a polynomial time solvable, polynomial time dynamic programming approach for them. Now what we'll do is, if a component have vertex with degree at least 4, then simply we'll branch on the vertex with degree 4 or more. That was a rhyme, 4 or more. Then we will branch on the vertex with degree 4, and the branching vector will come out to be 1, 4. Now, if the component have at least 1 degree 1 vertex, then for this A case, we already know that it's polynomial time solvable. In this B, we will just branch on X, and the time complex and the complexity will come out to be 2, 3, since the branch on X will be 1, 3. But in the case when X is in the solution, the remaining graph containing V and U will become a path and is polynomial time solvable and will give at least one size vertex cover. So that case will become 2. So it will be eventually 2, 3 branching. Now in this C case, we'll again branch on X, since we know that in the case when we branch on X, it will be 1, 3 branching. But in the case of 1, when we pick X in this solution, the remaining graph will give a 2, 3 branching, because in this B case, we knew that. So it will eventually become 3, 4, 3. And in this D case, we will branch again on Z, So the remaining graph, as we know, that the remaining graph is from if when we branch on Z, it will be 1 comma 3 branching, but when Z is in the solution, the remaining graph will give at least one size vertex cover in polynomial time, since we know from the case A, so it will be 2 comma 3 branching, and same as for the remaining cases. So overall branching vector for a component having at least 1 degree 1 vertex will be 3 comma 4 comma 3. Now for a component having a triangle, so in this A case, it will be polynomial time soluble because as said, it is of limited size. So we can check for all the possible combinations of vertices and it still won't take much of time. So moving onwards to this B, if we branch on W, then in the case when W is in the solution, the remaining V and U will become a path, and we can easily find out which and we know that for path we can solve this as a CSVC in polynomial time. So it will be in eventually 2 comma 3 branching. In the C case, we'll branch on similarly we'll branch on W, and the remaining graph, when the W is picked, the remaining graph will give us a branching vector of 2 comma 3. So overall our branching vector will become 3 comma 4 comma 3. And similarly in D case, when branch on W, where W have the least neighbor in X, when neighborhood of W is in the solution, then we know that neighborhood of U and neighborhood of V will also be in the solution. So even its branching vector will become 1 comma 4. So overall the branching vector for components having a triangle will be equal to 3 comma 4 comma 3 because it is the first branching on all these four cases. Now let's come to component having degree 2 vertices. So in this A case, we simply branch on W, and we know that when W is in the solution, this U, V and V, this remaining graph, sorry, that was a misprint there, V came twice, but you understand, when W is in the solution, the remaining graph will give us a branching vector of at least 2 comma 3. So the overall branching vector will be 3 comma 4 comma 3. And in the second case, if the neighborhood of U in X are less than equal to neighborhood of V in X minus 1, then we branch on neighborhood of W, and if neighborhood of W is not in the solution, then we pick W and U both in the solution. Detailed explanation for this is in the paper because it's a like little complicated case, but you will understand it. It is explained in detail in the paper, so go have a look at it. And then so overall branching vector for this component having degree 2 vertex will come out to be 3 comma 4 comma 3. Now let's look at component having all degree 3 and degree 2 neighbors and vice versa. So first of all, in this A case, we know that it's of limited size, so it is polynomial time soluble. So we won't be like picking any attention to that, giving any attention to that. Now let's move on to this B part. In this one, we'll branch on X and U, and it will come out to be branching vector of 3 comma 4 comma 3. In the next case, we branch on X and W, and when they both are in the solution, so in that case, the remaining graph between those two will become polynomial time soluble and will give at least two size vertex cover. So it will be 3 comma 4 comma 4. And so for the D and E part is same will apply, and the overall branching vector for this will become 3 comma 4 comma 3. Now the remaining all components, first off is this A part. In that we branch on Z and P, and then comes the B part in which we branch on neighborhood of V, neighborhood of Z, and when both of those are not in the solution, then we branch on VZ PQ. And similarly for this C part, we branch on neighborhood of Y, and if that is not in the solution, then Y and neighborhood of Z, and if that is also not in the solution, then Y, Z, and X. So the worst case time complexity for all the remaining component are 3 comma 4 comma 3. So the overall branching vector for the rest of all component will be 3 comma 4 comma 3. Now as we have seen, the or from all the different components, our branching vector came out to be 1 comma 4, and 3, 4, 3. So the first one is 3, 4, 3, which gives us a time complexity of 1.3953 to the power k. Now let's go to sparse feedback vertex set kernel. So we follow basic principle, which has bound the high and low degree of the graph and then bound the number of vertex in the graph. So first of all, we start with mark the vertex having k plus 1 flower as m. So what is a flower? Uh, so in this example, if you see it is a 4 flower because u is a vertex and there are 4 cycles that passes through u and only u. Like they passes through other vertices, but they intersect only at u. So if you see C1, C2, Ci and Ck, they all passes through u and they intersect only at u. So it is a 4 flower passing through at u. So what we'll do is we'll add a self loop for each such vertex that have a k plus 1 flower. Then let's come move forward. Then we go to delete vertex having degree 1 in G minus M. So in this graph, if you see 4, this is a degree 1 vertex. And since we are talking about feedback vertex set, 4, I don't think 4 is participating in any cycle. If you feel that, then raise a concern with me. And then 4 is, since 4 is not in any cycle, then we can simply delete 4 and it won't matter to us. So all the cycle will still be preserved. So now if two unmarked degree 2 vertexes are neighbor, then delete one. Since the since for example in this you see u and v both are unmarked and they have degree 2 with the unmarked vertices. Like I'm not saying they are overall degree 2, they have degree 2 with the unmarked vertices. They may have more neighbors in marked vertices, but we don't concern that. So what we will do is in this case, it's better to keep v than u since we have to keep the number of edges minimum in the solution. If in case future we have to pick one of them, then it's better to pick v than u since all of the cycle in the unmarked part are already passing through all of the cycle that passes through u in the unmarked part also passes through v. So it's better to keep v in our solution than u. So what we'll do is we'll remove all the edges between u and its unmarked neighbors and connect its other neighbor with v. And now from the literature, we know that for a graph H, a vertex v belongs to VH without a self loop and an integer k. There is a polynomial time algorithm which either outputs a k plus 1 flower at v or correctly concludes that no such k plus 1 flower exists. Moreover, if there is no k plus 1 flower at V, it outputs a set ZV subset of VH minus V of size at most 2k such that ZV intersects every cycle containing V in H. Now for each vertex in G minus M, we find ZV. Our graph looks something like this for a vertex V. So this capsule shape is what we call a component. A component is a portion of the graph that is connected directly to V and is not ZV. So now now we see this red cycle that you see. So we find k plus 1 such components that have this red cycle. If there are more than k plus 1 there's such component, then we say that this is a no instance, or if there are less than, because each of these components are disjoint, and if there are k plus 1 or more disjoint cycles, then it is a no instance of FVS, hence it is also no instance of CFVS. So we mark we mark all the component having an internal cycle. Then there might be a cycle between V and ZV. So to cover those cycle, we mark all the ZV and also V. Now for each vertex in ZV, if that vertex has two neighbors in single component, so we mark k plus 2 such components. After that, for each vertex in ZV, we mark k plus 2 components having single neighbor with ZV. Now for each combination of vertex in ZV, we mark k plus 2 components that have both of those vertices as its neighbor. So if there are two vertices in ZV, Z1 and Z2, and if there is a component C1 that is connected to both Z1 and that has edge with both Z1 and Z2, then we mark k plus 2 such components. Now, after marking all these components, we delete the edge between V and all the unmarked components. So this orange or yellow edge that you see, we delete all those such edges. So now since we know that how many components and vertex we have marked, so that's why we know that how many edges are remaining with V. So the degree of vertex in G dash is bounded by order of k cube because for each V we repeat the above process. So now let H be a graph with minimum degree at least 3 and maximum degree at most delta, then a feedback vertex set of size at most k, then H has at most delta plus 1 into k vertices and 2 delta k edges. And this is from known literature. So number of vertices in G is m plus G dash, which is equal to order k to the power 4. So let's come to sparse feedback vertex set. We define a new variant of the problem called constraint sparse feedback vertex set. Let's just say that both of them are equivalent that we have proved have shown in the paper. So first, what we do is find FPS Z of size at most k in 3.592 to the power k using the existing literature. If we can't find an FPS of size k, then there clearly does not exist an SFPS of size less than or equal to k also. Then split Z in two set x and y such that x union y is equal to z. And for each possible pair of x comma y, solve CSFPS separately. Now what CSFPS is, given input a graph G to set x subset of V and y subset of V and two integer k and t, such that number of connected components in GY is at most k and G minus x union y is acyclic. So now the question is, does there exist a set long subset of V, a subset of G minus x union y of size at most k minus x, such that S union x is a minimal feedback vertex set of G, and the number of edges in G, graph induced on S union x is at most t. So we define a budget mu is equal to b plus c minus g. Initially mu is less than equal to 2k. So how we say that is because b is equal to k minus x, and since x is subset of z, so it can't be more than k and less than 0. So b can be at most k and at least 0. And c, number of connected components in gy, since y is also a subset of z, which was of size at most k. So size of y itself is constrained with k. So number of components in y will also be at most k and at least 0. Now the g is the number of vertices in uh, neighborhood of v, such a subset of x union y. Uh, and v belongs to g minus x union y, and neighborhood of v in g intersection y is equal to 2, which means that the vertex v in g minus x union y have only two neighbors in g minus x, and both of those neighbors are in y. So now either that vertex will go in the solution, it means, and either go in the x, then which will reduce b by 1, or will go in y and reduce the number of component by 1, so reducing c by 1. So when b plus c will become 0, and if there is still g left, then we know that it is a no instance. So if mu is less than 0, then this is no instance of CFES. because each vertex of G will either be reduced by 1 or reduce B by 1 or C by 1. And since B greater than B plus C, G greater than B plus C, so even when B plus C becomes 0, there will still be G left. So this is a sample graph. And X, the G minus X union Y is here mentioned as H. So first, if there are 2 degree 2 vertices in H union Y, which have one neighbor in H and one neighbor in Y. Specifically, I'm mentioning like these two vertices which are degree 2 in H union Y. They may have more neighbors in X, but they are degree 2 in H union Y, and one of their neighbor is in Y, and the other neighbor is them himself. So there's an H between both of them. So what we do is, since all the cycles in H union Y, this passes through one, also passes through other. So what we do is, we pick the vertex which has more neighbors in X. So since this left upper vertex have more neighbors in X, so we pick this vertex and we shift it to Y, and we keep the other vertex in H. So since after this vertex, which with more neighbor in X goes to Y, there won't be any number of component increasing in Y, since it only has one neighbor and it has one neighbor. And but this vertex in H will become a good vertex which will increase the G, eventually reducing B plus C minus G is equal to mu. So via this, we can guarantee that mu will decrease by 1 for sure. So after that, our graph will look something like this. Then we will mark, then we will look at the vertex which has two neighbors in a single component in Y. And since Y can, none of the vertex from Y will go in the X, so we know that this marked vertex, this vertex must go in X, since the cycle only passes through Y and this vertex. So to cover this cycle in FES, we have to take this vertex in the solution. So now our graph will look something like this. After that, if there exists a vertex in H such that neighborhood of that vertex in Y is greater than equal to 2, and neighborhood of that vertex in Y union H is greater than equal to 3, then we will branch on that vertex. So for example, this vertex, it has at least two neighbors in Y and at least three neighbors in H union Y. So basically this is our overall requirement. So if there exists a vertex, then what we can do is we can either add that vertex to Y, which will reduce the number of component by 1, or what we can do is we can add that vertex to X, which will reduce B, which is K minus X by 1. So in both the cases, there it will be 1 comma 1. So the branching vector for this case will be 1 comma 1. So after dealing with those vertex, now if there exists a leaf vertex in H, so just FYI, this graph is not exact representation of the vertex are not the same as in the previous slide. So if I'm mentioning this graph right now, this does not have to be the same as the previous one. So this is just a pictorial representation of the branching that I'm mentioning right now. So if there exists a leaf vertex in H, so let this left bottom vertex be a leaf vertex in H, and which is farthest from the root, and let this other vertex be its parent, then we can branch on P. So if we take P, this vertex I'm referring as P because it's parent. So if we branch and take that vertex in X, then then B will reduce by 1. So it is good for us since mu will reduce by 1. But if we take that vertex back and we add that in Y, then number of component might not change, but that other neighbor that was that the node that was its child Since it now has exactly two neighbors in Y and no neighbors in H, it becomes a good vertex, and hence it will reduce mu by 1 by increasing G by 1. So now our graph will look something like this, which will only contain good vertices. So what we will do is we will pick a vertex which has the most neighbors in X, and we will add that to Y. Uh, so so this will reduce the number of component in Y by 1, and we will keep doing that until there is a vertex. So as you can see here, this vertex now it has two neighbors in the same component in Y, so this must go in the solution X. So we'll take that in the solution, and we keep when we will repeat doing that until we either there is no component, there's only one component in Y, or all the components in H have the their neighbors. All the components in H have their neighbor in the same component. So after repeating this again and again and again, we will eventually exhaust with all the vertex in polynomial time. So initially, mu was equal to 2i, and in each step, it directly reduced by 1, or in branching, it was reduced by 1 by making branching vector 1, comma 1. So worst case branching vector was 1, comma 1. So time complexity for CS, pay attention, time complexity for CS FPS was 2 to the power 2i, which is 4 to the power I. But now let's come to time complexity for sparse feedback vertex at SFPS. So its time complexity will be a time to compute FPS plus the time to compute to solve CS FPS for each permutation and combination of X comma Y. So its total time complexity comes out to be 5 to the power K. Now for the future scope, the problem itself can be expanded into density and covering solution, and also a parameterized approach can be thought of with parameter T also. So if there are any question and answer, I will be ready to take them for now in the comment sections. And thank you.